Log on, tune in, find out. Another good idea from Cambridge.
Thank you, Professor Wallace, for your kind introduction and for inviting me to visit Newton Institute and for asking me to give this talk. I would also like to take this opportunity to thank Professor Newstead and his co-organizers for inviting me to participate in this activity on moduli spaces. So, this is the title, the stability and its ramifications. See, what I want to talk about is mainly interaction between algebraic geometry and other major fields of mathematics like number theory, differential geometry, PD and so on, and also physics. So, what I will do is in the first part of my talk, I will talk about some very old interactions starting already from the time of Riemann, and then explain in what directions this interaction took place in all these fields. And then the second part of my talk, I will confine myself to a particular topic in algebraic geometry, namely the notion of stability, which most of you are familiar with, and this interaction which is very active with the other fields of mathematics and physics. So, this is the second part will be the notion of stability, how it arose in mathematics and what is the relationship with other topics in PDE, differential geometry, number theory and so on. Okay. These relationships between these fields were already present in the work of Riemann on abelian integrals, which as you know started a new era in modern algebraic geometry in about 1850s in his work on abelian functions. And appropriately enough, it started with a problem in analysis of integral calculus, namely to study these integrals of the type Rxy dy dx with some x and y satisfying some polynomial relation. So, in particular elliptic integrals, you know, you are familiar with dx by square root 4x cubed, whatever, and also the multivalued functions which arise from this. So, this was the problem that Riemann was interested in it, and Riemann studied the problem of existence of these abelian integrals or differentials, as we say these days, with given singularities and periods on the Riemann surface associated with the algebraic curve. So, if you take f x y equal to 0, you can associate a certain surface with that two-dimensional surface on which you can talk of analytic functions, and then Riemann studied abelian integrals and differentials on this. You recall that period is integral of the differential form on a loop. So, it is very explicitly a problem of integral calculus. That is what he started with. Now, for the proof of this existence theorem, as probably most of you know, Riemann used Dirichlet's principle, namely the construction of a harmonic function on a domain, say a bounded domain, say in plane, with given boundary values. So, you have a domain G, I think I can use the board. So, you have some domain D and this D, and you are given a function say G on delta D. Your problem is to find a function u in D, so that u restricted to domain boundaries G and Laplacian u is 0. So, this is the Dirichlet problem, and Riemann used this that the possibility of solving this Dirichlet problem in his proofs, and he used what he called, I think, Dirichlet's principle, though it was known to others earlier. This is the following. So, suppose I want to find this harmonic function u. So, you take all functions v, not necessarily harmonic, in D, so that v restricted the boundary is or smooth functions is G, and look at this Dirichlet integral dv by dx square plus dv by dy squared dx. So, take all functions v which takes the boundary value g and look at this Dirichlet integral, and the claim is, Dirichlet principle is, there is a function u which attains minimum of this, and that function is harmonic. This is the Dirichlet principle. But however, the existence of minimum is not clear. I mean, if you assume there is a minimum is attained for a function u, it is easy to check its harmonic and it does whatever you want, more or less. And Riemann assumed the minimum exists and then went ahead, and then it was soon pointed out by Strauss and others that it needs a proof that there is a minimum. And Weierstrass gave some natural kind of extremal problem for which the minimum does not exist. So, anyway, I mean, Riemann went ahead, and I mean, this reminds me of some saying of D'Alembert. When a young person said, I cannot prove it yet or something, he said, go ahead, faith will come to you. Allez en avant, la foi vous viendra. Like this, he just assumed this is okay and then went ahead, of course, the theorems. But other people were a bit concerned, they wanted to prove it. After all, you want to prove something, why should I bother about Dirichlet principle? You may have other methods. And this is what Schwarz and Carl Newman did. They found other methods in which to solve the Dirichlet problem and all the whatever Riemann's existence theorem. And it is in this process they discovered, for example, use of potential theory in elliptic differential equation and so on. It was first used in this context, and also the famous alternating method of Schwarz was also introduced precisely for this purpose. So, this is the first example of a sort of what is now we will call algebraic geometry problem, which gave rise to even some developments in PDE. That is the first. So, this is what I said. The methods invented by these two people, for example, Schwarz and Carl Newman, they were turned out to be relevant for differential equations, for example, the use of potential theory and so on. So, this is the first sort of direct influence of Riemann's work. Now, after a few years, after some time, quite a few years, actually Hilbert proved the Dirichlet principle that this minimum is attained, and then you can do whatever you want with this. But again, this again was a very important development for PDE, not so much probably for Riemann's theory, because this is what gave rise to what they used to be called direct methods of calculus of variations. And actually, from the modern point of view, this initiated Hilbert space methods in PDE. That is the first important thing in that what Hilbert did. No, I mean, for example, the so called method of orthogonal projection for PDE and also in sublevels spaces and all can be traced these kind of ideas originally. So, that was another consequence of trying to fix Riemann's proofs by analytic methods. But then there was another group of people who said most of the theorems are more or less make sense algebraically. Why should I need any analysis? Let me try to prove them without any analysis. That is the next development. So, this is a so called algebraic study of function fields. Now, it started with Dedekind and Weber. So, they tried to give a purely algebraic treatment of the work of Riemann, avoiding analysis. This is what they did. And now, what you will call algebraic study of function fields. Now, there is one importance, already an obvious importance for this study. This is what gave rise to starting point of algebraic techniques for algebraic geometry. That is the first one. But I think even more important, from this point of view, the profound analogy between algebraic geometry and algebraic number theory becomes clearer. So, that is the important. So, already you see the relation, and more precisely the case relation between Riemann surfaces and algebraic number theory. So, that was the real one of the important outcome of the work. Now, of course, Andre Weil was one of them who emphasized this relationship between number theory and algebraic geometry, and also he popularized this analogy, and he was fond of what is called Rosetta Stone analogy, which you might have seen. I will explain that. So, this is the Rosetta Stone, which is in the British Museum. As you enter the almost British Museum, you see that. Now, for many years the Egyptian hieroglyphs were not deciphered, and they were deciphered by Champollion, and one of the things which he needed to decipher that was the stone, which was discovered in the Nile Delta area in a place called Rashid, and then the name sort of transported to Rosetta. In French, Rashid was translated to Rosetta or whatever. So, that is the Rosetta Stone. So, the point of that is, so this stone had inscription in 3 languages. The one below was in Greek, which was the language of the ruling class at the time, and the middle one was in Demotic, which is the language of the popular people, and of course, hieroglyphs, of which at that time one knew nothing. But however, since they could understand these two, Demotic and Greek, quite a bit, some of them, they found the same message was written in both of these, and therefore, of course, they guessed the third one should also must be the same message. So, this helped Champollion to decipher this. So, Andre Weil again and again is very fond of this analogy. He says, okay, according to him, number theory is the most difficult thing. We do not know much about it. Okay. Riemann surface, we understand everything more or less. Okay. We are the ruling class though at the moment, so we understand everything. The function fields is the one which came by the work of Dedekind and Weber and so on, which I was talking about. So, it is somewhere in between. I mean, let us say function fields is geometrically nearer Riemann surfaces and algebraically nearer number theory, whatever it means. Let us think of it this way. And therefore, his idea was the techniques and results in one field may give insight into the other one, possibly passing through the middle one, which is nearer to the first one and the last one. So, he was very fond of his analogy. I am sure he also used it very much. Anyway, I remember he once writes it to his sister a letter giving her some idea of mathematics, this Simone Weil, and he says at some point, goes on explaining something, and he says, well, I do not think you will understand what I am going to say, but anyway, I will continue writing to you, he says. So, anyway, in one of his letters also to her, he also talks about this. He seems to have been very fond of this analogy. So, this is the analogy which Andre Weil always, I think, had in mind and maybe used effectively. So, this again to say that the theory of Riemann surfaces with algebraic geometry from Riemann is related to number theory and of course, algebra. So, this is what I had already said. Now, it so happens that problems in number theory has given rise to some important development in techniques and theories of algebraic geometry. I will explain later maybe. And also, these results in turn provided tools to solve problems in number theory. You know, many examples of very famous problems have been solved recently by using inputs from algebraic geometry, growth and decay and others. Okay. Now, so after the work of Riemann, which is in say one complex dimension, naturally people try to extend these results to higher dimensions. Then already work of Picard and Poincaré would try to do it in 2 complex dimensions. But largely a part of complex analysis. For them, it was a part of complex analysis. And also for Poincaré, it was his study of algebraic geometry was partly a motivation for developing topology, algebraic topology. And in studying in one dimension studying integrals, he was studying multiple integrals. And I think it is known that he made some statements, Poincaré, which Elie Cartan interpreted as what we now call de Rham's theorem. So, it's already there is a statement which is somewhat obscure, but Elie Cartan interpreted this as de Rham's theorem and gave it to his then student de Rham as a thesis problem. But this statement is already there. Now we can understand, now we know what he was talking about, we know de Rham's theorem, we can understand the statement. But it should have been a bit difficult at that time to understand the statement. So, already you see algebraic geometry, topology and so on. Then of course, the work of Hodge on harmonic forms. Here the main point is whatever harmonic forms are, it is the application of theory of linear elliptic partial differential equation on manifolds. That is the whole point of Hodge. And with this analytical techniques, he proved things which are purely topological, like so called Lefschetz theorem, which at that time could not be proved either by topological methods or purely geometric methods. The only proof is by analysis and PDE. Now there are proofs which are very complicated, somewhat not very direct, but at that time this was the only proof, that is using analysis. Then there was work of Codera, and he used harmonic forms and differential geometric techniques to prove deep vanishing theorems, which play a key role in algebraic geometry. I will not go into that. Then the work of Codera-Spencer. It is very interesting to see the work of Codera-Spencer. In fact, my early days, that is what I studied first. It is supposed to be a problem on deformations of complex structure and algebraic geometry, but the basic techniques are from elliptic PDE. You see, all existence theorem, semi-continuity theorem, everything will be proved by elliptic PDE. So, it is a kind of Hodge theory with a parameter, essentially that is what they did. And of course, vanishing theorem, I mean even now I think it is one of the deepest results, I would say, Codera vanishing theorem. And essentially the only good proof is by analysis. Anyway, there are proofs, but then, so this I am trying to say how Riemann's work took off in the direction of analysis in higher dimensions. The work of Hodge, work of Codera, Codera-Spencer, and then it used analysis, but in turn the Atiyah-Singer index theorem on index of linear elliptic operators. So, a elliptic operator between 2 vector bundles, say on a compact manifold, then take the kernel, co-kernel, difference of dimension, you want to compute that number, this index. Now, of course, people say, oh, it should be computable something, but what is the correct statement was suggested by Riemann-Roch theorem, which arose in algebraic geometry, and is a main input is the Todd genus, the Todd class, which really arose in algebraic geometry. So, you could not have even I think stated the theorem, what is the correct theorem for index, even though it is just a question in PDE without that. So, this is the influence, it is a direct influence of algebraic geometry on PDE. So, here are some of the players, you can recognize all of them: Picard, Poincaré, Hodge, Codera, Spencer, Atiyah, Singer, and so on. So, I mean, okay, do something if you don't take it too seriously. So, in some sense, Riemann's algebraic geometry gave rise to differential analysis and manifolds. Already in the work of, let us say, book of Hermann Weyl made it clear, and PDE differential geometry, okay, like vanishing theorems, number theory. I will say more about number theory and algebraic geometry later. Now, what about algebraic geometry and physics? I have not told you much so far. Let me say something about that. Just make two comments. One, of course, Dirichlet principle certainly came from physics. It was already, many people like Kelvin and others knew this. That is how harmonic functions are to be solved. But even more, some people believe that Riemann even got his theorems and results from his physical intuition, and also got the methods of proof from physical intuition. At least Felix Klein believed this, and he has even written a book, how Riemann could have guessed the theorem by fluid blow or something like that. It is an interesting book. So, well, anyway, it is possible that he got it from physical motivation. Certainly, Dirichlet principle is from physics. So, that was at the early stages relation with physics. So, according to Klein, Riemann discovered many of his results and also his methods of proof by physical intuition. That is what he says, and he tries to substantiate his claim. It is not clear how Riemann thought, but anyway. So, this is the sort of my first part of my talk, where generally how from the time of Riemann this interaction between number theory, algebraic geometry and other fields developed. Now, I come to, now we will restrict ourselves to a particular area of algebraic geometry, the stability, which most of us know, but I will recall, because there will be some points which may not be known to the younger people, because they learn it in a different way. So, I want to say it in that way. Now, so what is this stability? Where did it start from? Okay, I will not make a big difference between semi-stability and stability. I mean, this is a kind of technical thing. When I say stable, you know, it's semi-stable, whatever, doesn't matter. Now, it occurs in the celebrated work of Hilbert on invariant theory first. I am going to explain this. Now, in his famous papers on invariant theory, Hilbert proved three basic theorems in commutative algebra, what we call commutative algebra, which is the basis of many things in algebraic geometry. So, called Hilbert basis theorem, Hilbert Nussdorf and Sichdis, whatever they are, we do not care at the moment. Now, what is invariant theory? Okay, let me just say this. Suppose you have the full linear group or special linear group acts on a vector space. Okay. It acts on a vector space. Take the polynomial functions, it also acts on that vector space. Now, you can look for invariants of that. I mean, one of the classically, slightly generalized this, I mean, classically what people do is you take, say, SL n operating on Cn and take my vector space to be some polynomials in Cn, and look at the representation SLN on the polynomials in Sm, and then look for polynomial invariants. So, this is the classical thing, and more generally we can say like this. And one of the basic problem was, so polynomial ring, you have subring of the polynomial ring invariants is the ring finitely generated. That is essentially, can you find a finite number of polynomials, invariant polynomials, so that any invariant polynomial can be written as a polynomial, in that maybe with relations, that is the problem. So, you have a ring of invariants. So, can I find finitely many polynomials, so that any invariants, any invariant polynomial, so that any invariant can be written as a polynomial in this. Hilbert proved yes for this group, GLN and SLN. But now comes this, which probably, but there was a criticism by people who have been looking at, for example, binary quadratic binary forms and so on. They said, okay, I mean, you just say there is a finite number of invariants, but can you give us explicit generators? That was the question. And there was a criticism which Jordan was one of the experts in invariant theory. He said, this well-known quotation, but he said what Hilbert is doing is not mathematics, but is theology. That's what he said. But by the way, it's less well known that after some time, the same Gordon said, I realize now that theology has also its uses. That's what he said after some time. But anyway, so the problem is, okay, then Hilbert wanted to counter this. So he says, okay, at least I'll give some procedure how one can try to determine a finite number of generators. I mean, that was the motivation for him to define what we nowadays call non-semi-stable points. Forget that terminology, which is a bit awkward. Hilbert called them, Hilbert defined the notion of the so-called null form. This is what we will call non-semi-stable these days. So, this is it's a point in my vector space V on the projective space where more or less all invariants vanish. More precisely, if all non-constant homogeneous invariants vanish. This is called a null form. So, semi-stable means it is not a null form, which means roughly there is at least one invariant, you have to be somewhat careful in saying it, which does not vanish there, homogeneous non-zero invariant. So, semi-stable is not a null form. But I mean, why was he interested in all this? So, this idea is this: you take this null forms, NSS or something, null forms. I don't know, I call it NSS, I don't remember. Do you have a terminology? Let's see. Yeah, NS is null cone. And look at it in the projective space in Pn. So, yeah, so he did two things first. He gave a certain procedure, which I will say, which is called Hilbert-Mumford criterion, to decide when such a point is a null form. So that this set we understand to some extent is an algebraic variety. So, if you know a certain set of polynomials or whatever which vanish on this, from this I can fabricate my invariants. That was the idea. I can make it more precise if you want later. So, knowledge of this variety NS gives information about the generators. Of course, you should know what this variety is. That is what for him Hilbert-Mumford criterion gives, and you can get a set of generators more or less from this ring of invariants. So, yeah, in Hilbert's mind, this has answered the criticism of being not too explicit. That is why he studied this and gave this, but Mumford completely turned it around. He turned in some sense Hilbert on its head. He said, for me the interesting point is not these null forms, but the complement. Now, why was he interested in this? It is so the complement of null forms is what we will call semi-stable points. So, complement of null forms is semi-stable. In projective space or whatever. Now, he was interested in the complement for this following reason. Now, first of all, I make some general remark. Construction of quotient space in algebraic geometry is a very subtle problem. I can't at the moment say why. So, it is in some sense the quotient may exist in all good topological sense, even the analytic sense and what not, but it may not exist as an algebraic variety. So, it is a subtle problem. Now, what Mumford observed was not very difficult, but fundamental observation is you take the complement of the null forms, that so called semi stable points, then the group G operates on PSS, you can check easily, and there is a whatever it means a good quotient, you get a nice quotient which is a compact variety, that is the point. So, what happens is most of the moduli problems you find such a space and form the quotient, that is the so called moduli space. So, moduli problem is, for those who are not sort of familiar, this simply means classification algebraic varieties. How do you classify algebraic varieties with such given numerical invariants? That is the problem. Anyway, that is the. So, the main observation of Mumford is it is the complement which is of should be of interest, and the fact that you answered some criticism is not so important. And it's also very surprising, this paper is one of the last papers of Hilbert. This was not so much in vogue. Well, all the other papers were studied and you know, everything was taken out of these papers. Mumford is the one who really saw the importance of the complement. Not what Hilbert himself was interested, but the complement is the one which is going to play a big role. So, this is so in other words, this notion of semi-stability in some sense arose in a purely algebraic context or something like this, and Mumford found this is the real key to solve classification problems in algebraic geometry. But in spite of but what are the semi-stable points or what are the null forms? In spite of Hilbert-Mumford criterion, it is not an easy problem. In every case you have criterion, but to just pin it down, it is not so easy. That is one of the main troubles. So, let me say something about the moduli problems. So, it is a classification problems in algebraic geometry. I mean, what does it, for example, you take all compact Riemann surfaces of a given genus, that is, take a compact orientable surface, topological, and ask how many complex structures are there on that. That is the first question. One. The other one is a ruled surface. See, nowadays people do not think of ruled surface because essentially this is same as Riemann surface vector bundles. Ruled surface is something which is surface like this, and then fibered by P1s, projective lines. With a fixed, say, this x is some base is Riemann surface, say, compact. And it was a big problem for many years, solved satisfactorily only in the 60s, to have a good classification of ruled surfaces. And that is same as in the modern language, essentially holomorphic vector bodies in a compact Riemann surface. Now, Riemann. So, this theory of holomorphic vector bodies in a compact Riemann surface is in a way a non-abelian generalization of Riemann theory. See, Riemann was only looking at integrals, integration over cycles or something. It is really you are looking at only the homology group. But here this will look at even the fundamental group. So, it is a kind of non-abelian, obvious non-abelian generalization. So, the other example is subvarieties of projective space. I mean, for example, you take all hypersurface of a given degree in a projective space, you identify two of them, if you can take them one to the other by projective transformations, is there a good quotient space and so on. These are the problems. So, subvarieties of a projective space. However, what all this experience showed, so see, Mumford's observation was you can get a good quotient on semi-stable points. So, you have to know what are semi-stable points, only there you can expect a good moduli solution to moduli problem. And therefore, what this teaches us is, if you want to classify, say, all varieties of subvarieties or something like this, you can't hope to do that. You have to pin down a subclass which we will call stable or semi-stable. Only those you can try to classify. That was the moral. Of course, you have to find what are these objects. Hopefully, Hilbert Mumford will give you some clue if you can calculate it. So, that is the whole philosophy, but the kind of answers you get are not very intuitive. Let us go there. So, I will just repeat first part. So, the construction of moduli spaces reduces to construction of quotients, and this what I should have called what Mumford did is called geometric invariant theory or GIT. So, the GIT gives a way of identifying good objects, and these are objects which correspond to so called stable points. Calculation of stable points is not easy, even though there is a criterion in principle, sometimes it is not so easy to calculate them. Now, anyway, doing all this, what Mumford did was he found out what is a good notion for a vector bundle on a Riemann surface. So, for example, a vector bundle of degree 0 on a Riemann surface is called stable if the degree of all sub bundles is less than 0. In some sense, every sub bundle is less positive than the whole space. It is a purely algebraic condition. The main point to remember is this is an algebraic condition. It is a purely algebraic condition. Okay. Now, these kind of algebraic conditions which you get out of GIT, I mean sometimes you do not understand the significance. You will need some other interpretation to understand what is going on there. And I mean this is where the relationship between this purely algebraic notion of stability its relation to differential geometry and partial differential equations come in. So, you remember Mumford defined something called a stable bundle, okay, of degree 0. Let us forget some algebraic condition, just keep it in mind. It was not clear what it means. Then several years ago, Seshadri and I proved a theorem. It says your vector bundle of degree 0 on a compact Riemann surface comes from a irreducible unitary representation of the fundamental group of the surface, if and only if it is stable. So, the only thing to have in mind here is stable is a purely algebraic geometric condition, makes sense in any characteristic if you wish, while the fundamental group is a very transcendental object, it is not a algebraic object at all. And you can also formulate it in terms of flat unitary bundles, corrections, curvature and so on. That is the equivalent formulation. So, this gives you some insight that purely algebraic condition is a differential geometric condition, and once you see this way, then you can also see what happens in higher dimensions. That is, when the base manifold is not a Riemann surface, you can still define stable bundles more or less the same way. What do they correspond to in a geometric way was the question, and this was not quite obvious. This was conjectured, the correct result was conjectured by Hitchin and Kobayashi. So, what they did was, I will not write it down, maybe later if I have time I will do that. So, you have Wallenbach vector bundle on a say projective variety, then you have metric, so maybe I write something, not very much. So, M is projective, some projective, E a Wallenbach vector bundle on M. Then you take a metric on E, Hermitian metric. Then this gives a certain connection, so called Chern connection and curvature. Now, this Hermitian Einstein is a condition on the curvature. I mean related to the embedding. So, you have a Kähler metric on M, do not bother what is this. For example, lambda f equal to some scalar into identity or something. Anyway, it does not matter. It is a condition on the curvature, and okay, I will say later about that. So, you have to find such a metric, and in fact, this was proved. And so, the conjecture was more or less Hermitian-Einstein matrix exists if and only if the bundle is stable. Well, to be more precise, for those who know, not stable, polystable, forget it. Essentially, so the stability is an algebraic condition, Hermitian-Einstein is a purely analytical condition, and this is stable if and only if it is Hermitian-Einstein metric, and which in the case of Riemann surface reduces to the earlier theorem. And this conjecture was proved by Donaldson, and in the projective case and Kähler case, okay, by Uhlenbeck. So, the whole point is you have to solve a nonlinear PDE now. I mean, why does nonlinear come in here? See, so far Riemann theory and others said linear PDE. See, that is, if the vector bundle is of rank greater than or equal to 2, you will be working with some UN or something like this, or GLN or something. Now, the curvature involves Lie algebra multiplication, the Lie algebra of UN, that is, I mean, non-abelian. So, that gives you a nonlinear term, the equation, the curvature being nonlinear in the curvature, the connection terms gives you the nonlinear equation. So, it is not so easy to solve this nonlinear PDE, and this is what they did. When Seshadri and I was working on this, we were aware we have to solve a nonlinear PDE, but we did not do that. We used a method which I will not go into, which is a fantastic method which was invented by Poincaré and Klein to solve the uniformization problem, so called continuity method. Actually, at that time they could not make that method work, but we were luckier, so we could make it work. So, it is a kind of global method, that is, before you start just here solving one PDE, you should know to some extent your moduli spaces before you can prove that theorem. So, this is the, of course, here are some of the people, this is Seshadri, this is Ichin, Kobayashi, this is Donaldson. So, here what I want to say is this purely algebraic notion of stability is related to differential geometry, and in order to get a kind of differential geometric objects, you have to solve PDEs which are usually nonlinear, and it more or less gives one-to-one correspondence between these two. Now, there are some problems. I will not talk much about these things because they are still very much, I think, work in progress, not by me, by others, and I think Donaldson will talk about it next week or this week. But just to give you some idea what these kind of problems are, I will just mention a few things. So, there is another problem, the so called existence of a Kähler-Einstein metric and a Fano manifold. Fano manifold is anti-canonical bundle is ample. Kähler-Einstein simply means Ricci curvature is the multiple of lambda j bar, Einstein kind of conditions. Okay, this is Einstein metric. So, you look at a Fano manifold, is there an Einstein metric on that? Question. Now, if you take if the canonical bundle is ample, yes, there is no stability condition. Here in general it does not exist, and it is believed that, I mean, more or less, you have to have a notion of a suitable notion of stability for a manifold, for this standard manifold, if it is so only, if and only if, like the earlier theorems. The similar one is, general problem is you have a submanifold of say projective space. What is a good metric on the projective space? I mean, taking into account the embedding and not the projective space, on the variety. So, the problem of existence of a good metric on the projective variety is also related to the notion of stability. So, for example, one way to state is you look for a scalar metric with constant scalar curvature in a scalar class, which is the same as more or less this problem. That is, what the best possible metric given the projective variety, what is the best possible metric which can make me precise? If so, does it exist? I mean, these are two questions, and these are related to the, in some sense, notion of stability. Now, here you see, so let me recall what is the situation here. We have a submanifold of a projective space, and I want some good metrics, and we say that it has to be, it should have some stability property. I claim what you have done is the following. So, you have come to the problem of deciding. So, okay, let me again say this slowly. So, you have a submanifold of Pn. You want to decide in what sense? In some sense, X is stable or semi-stable, submanifold, with respect to the action of the projective group. Now, okay, if you see, this is exactly the problem that Hilbert was worried about in the case of hypersurfaces. If you see this case which I said here, SNCN, an element here will define a hypersurface, and you are trying to see when is this point semi-stable in the hypersurface. This is what you are. So, as I'll not quote something. So, what has happened is, at the end of our exploring, we have arrived at where we started from. So, it's amazing that this problem, which is very much in the process of research, is exactly related, at least for the hypersurfaces, to the question of Hilbert. One would not have imagined that these are such a close connections. So, I will not say more about this, because I myself do not know exactly what is the situation now in this, and I will know from Donaldson and probably from Thomas sometime. So, now, so we can have a speculation now. See, what is it? The philosophy seems to be that if you want to solve some differential construct some differential geometric object, you need some algebraic condition stability. Or jumping a little further, suppose I want to solve a nonlinear PDE. Apparently, there is some hidden stability condition the differential equation itself has, that if only if it is satisfied, you can solve this differential equation. I think people have tried this. One way is to sort of guess what should be the Mumford stability condition, infinite dimensional, and so on and so forth. But in any case, one can have it as a working hypothesis. I think this is very important. That there is some hidden, in many cases, there are some hidden algebraic conditions. These have to be satisfied. And it's okay. I don't want to say more about it now. So that is speculation. Now, what about physics? I have still 5 minutes. I can say something. Let's see. 5 minutes. So, I mean, first is Yang-Mills equation is an equation for, it is in some sense the elliptic nonlinear generalization of Maxwell. Elliptic. No, of Maxwell. differential equation, which involves some un or something like this. Again, because of curvature, the condition for curvature, it is non-linear. This is the Yang-Mills equation. It's a non-linear equation generally. And we can see this in the case of Riemann surfaces, the flat unity connections are related to Yang-Mills, and therefore to stable bundles by the theorem I quoted. Now, Atiyah and Bott, after some years, took the other point of view and studied stable bundles from the point of view of Yang-Mills equation, and re-derived some of the results which was proved by algebraic and analytical methods, no, not analytical methods. So, that was the relation to physics, and also stable bundles and algebraic surfaces and anti-self dual connections and so on. This is a sort of thing which is very important in the work of early work of Donaldson on also in differential topology to understand differentiable structures and algebraic surfaces. And then there is something more which I cannot explain, I do not have time to explain now. There is a very deep connection between modular space of stable bundles and conformal field theory. That is, these are nice objects and nice manifolds, compact manifolds. Then you look at linear systems on them, and these are the precisely so called conformal blocks that the physicists were doing. And so, it is very interesting. Some physicists were to some extent influenced by what was happening in modular spaces. On the other hand, they came with their own insights from physics somehow, which gave us new problems for mathematicians. And they do not care to prove, but their job is to prove. So, we have to prove it. So, so this is the modular space of this is relation to physics. There are many more, but just I want to confine myself to say that these are still active. They are not just now. I think at the end I will come to number theory. Recall the Rosetta Stone analogy of Van der Waals, share by y, let us say. Okay. So, see, the idea is, after all, I know integers. How do I get a Riemann surface? What is the analogy or something? Essentially, what you do is the usual integers or integer number field augmented by valuations of the field is the analog of a compact Riemann surface. That is, if you have rational numbers, then you complete it, you get real numbers. You think of it as a new point. So, this is the analog of Riemann surface. Then you can study arithmetic bundles. It is not very difficult to define this. There are many interesting questions related to geometry of numbers, and there are some questions which people in geometry of numbers did not ask, could have asked, maybe even at the time of Minkowski, which we do not know the answer. And these were suggested by this analogy with stable bundles. You can define a stable lattice, you can ask tensor product is stable or not, semi-stable, all sorts of questions you can ask. But however, even without that, already it has been used very much in number theory. There are some, I have no time to say that, there are some canonical filtrations on these usual bundles. They can be generalized to arithmetic bundles, and then you can use this to stratify some spaces which occur in arithmetic, and it has been used very much already by number theories. For example, in the work on Stukas and so on. And finally, I just want to say one of the more recent ones, which again got a Fields medal. There was one earlier which also got a Fields medal. Some work which uses in an essential way the work of Hitchin, which generalizes the theorem which Seshadri and myself which I said, and that is one of the very important inputs in purely number theoretic questions. So, I would like to conclude by saying it's a topic which seems to be in deep relationship with completely different aspects of mathematics. On the one hand, PDE and so on, number theory. So, That's all I have to say.
Thank you very much. Well, we have a little time. Are there any questions or comments that people want to make? A remarkable mathematical tour that we've been exposed to. Any questions or comments for MS? If I can say, for someone who comes like I do from theoretical physics, I mean, there's something intuitive and obvious about stability, and it's quite hard translating that into the domain that you are talking about. Is it, I mean, this may be a really stupid question, but if I go right back to the Dirichlet problem, can you put in physics terms what stability, what mathematical stability is in that context, and would it actually connect with something that I would understand?
See, I do. There is something going on which I do not know myself. I'm sure there are people in the audience. I mean, you know this. Work of Douglas, the physicist, has been translated into mathematics by Briglett and others. It's called space of stability conditions. Mm-hmm. I don't know. There is some notion of stability. I'm sure that somebody here can explain this, right? What are the stability conditions?
I don't see any volunteers.
But more elementarily, you could draw a stable orbit in a vector space.
Yes.
And it would have a minimum and go off to infinity at both ends, and there'd be this stable minimum in the middle. I mean, okay. In some sense, that's the most obvious analogy.
Yeah. So, do I think of the stability as the fact that there is a variational principle behind that? Is that the framework in which I think of the stability, or is that wrong?
Yes, in some sense it is correct. In the infinite dimensional situation in this context. Right. In this.
Okay. Are there any other more sensible questions?
See, for example, Yang-Mills. You take the Yang-Mills. Take a minimum of that. That turns out to be a stable object in this sense. That's theorem in some sense. Yeah. So you take the Yang-Mills functional.
Yes.
Integral of
I do know that, yeah.
Yeah. And you take the minimum.
Higgs was my PhD supervisor. That's as close as I come.
Sorry. Then I don't know any physics.
Okay. Any other questions or comments?
I have one comment.
Yes.
Everybody in the audience knows, but this canonical filtration is known as Harder-Narasimhan filtration.
Known as the?
Harder-Narasimhan filtration.
Right. Good. Okay. Good. Well, if not, everybody knows that you're all invited to the reception outside, and let's thank our